Yeah, it's working, right? Yeah. Okay.
Hello, everyone, and welcome back. Thanks for being here for the last talk before the coffee break. This next presentation will be on Pass the Hash Toolkit for Windows Present. Sorry, my mistake. Just testing. This next presentation is actually on analysis and visualization of common packets. Packers. My apologies. Mr. Ero Carrera, before we begin, allow me to correctly and accurately introduce you. Ero Carrera is currently a reverse engineering automation researcher at Dynamics GmbH, formerly known as HIRBSecurity. Ero has previously spent several years as a virus researcher at HIRBSecure, where his main duties range from reverse engineering of malware to research in analysis automation methods. Prior to HIRBSecure, he was involved in miscellaneous research and development projects and has always had a passion for mathematics, reverse engineering, and computer security. While at HIRBSecure, he advanced the field of malware classification, introducing a joint paper with Gergely Erdely on applying genomic methods to binary structural classification. Other projects he's worked on include seminal research on generic unpacking. Certainly quite a mouthful, but ladies and gentlemen, do join me in welcoming Mr. Ero Carrera today.
Thank you. So today I'm going to talk a little bit about that last part that she mentioned, about generic unpacking and techniques, and about the specific techniques that Packers use to make our life more difficult. And I'm going to focus a little bit on some of the hard ones, on like Packers like to meet an armadillo, of some of the techniques they use to make debugging, tracing, reconstruction of the process the hardest. So first I'm going to give some sort of historical perspective, how we got here, how Packers actually came to be, right? So originally the idea of a Packer is exactly what the name says. They were meant to just like get an executable and make it smaller. They were aimed at, when you had like bulletin board systems and you wanted to like get binaries running around and still downloading something was, the size of it was important because you had to pay for bandwidth. So it was important to actually make it as small as possible. So that was the original idea of Packers. And they were something as simple as just compressing the executable and then creating a new executable that the first thing that it ran was had some sort of envelope that first decompressed the whole thing in memory. But they had no specific techniques. That they weren't aimed at obfuscating the binary. It was just like compression. Obviously, once you had this setup, it was really easy to go a step farther and actually improve on that. Because compression itself can be considered as some sort of obfuscation, because if you're not aware of the algorithm that is used, you will try to open the binary as it comes from file into some sort of tool, and you won't see the real code. The real code is, later on after execution, it exists in memory, but does not exist in the original binary. So although really, really simple, it could be considered some sort of obfuscation. So when they started actually to worry about protecting the binary, because they started charging money for the binary, so they started to put algorithms that they cared about. So they wanted to protect that. They wanted to protect intellectual property, and nowadays that's something that we see in all commercial applications. They want to protect the actual executable code because it contains algorithms or it contains processes that are important for the company that actually makes the application. So at that point, once you had that setup, it's really easy to think of ways of actually making it harder. Once you have something that takes control before the original application takes control, you can set up some sort of algorithms, some sort of techniques to actually prevent other tools from attaching to that process, dampening it or manipulating it, or actually looking at the real code. So I'm going to first go now through some of the techniques that have existed over time, some of them more recent, some of them older, in order to make the life of the analyst harder, or the life of the person who actually wants to look at the original code. Or not. Just a second. Everything has frozen, so okay, it's still alive. So Into the techniques. The most important thing at first, and this is really simple, is to destroy as much information from the binary as possible that would help you to get a clue of what it is. Specifically in malware, you want to destroy any sort of indication of the APIs it uses, because that exposes the functionality that it's going to use from the operating system, or any sort of strings. Pretty much anything that is clear text that gives you an idea of what the binary or executable might be trying to do, or might be information that might be using. If it's clear text, maybe email headers, maybe whatever might give you a clue of what the binary's purpose is. You want to try to erase and destroy that. So with a packer, with a compressor, that's pretty much taken for granted, because that's going to be compressed. It's not going to be clear text anymore. But still, the import table might be there, depending how you do the process of the compression. So if you want to actually protect something, you want to remove as much obvious information as possible. So one thing that all packers do is destroy and reconstruct later on the import address table in some way or another, because that exposes the whole functionality of the binary, the way it connects with the operating system. Depending how complex the packer is, they will just simply reconstruct the original table later on. That's really comfortable, because lots of tools then can just dump it, and you will have it in your memory dump, and with a little bit of work you will be able to load that into some tool and take advantage of that full nice import table. In other circumstances, in more complex packers, they will reconstruct it in a non-standard way. They would use different artifacts to, so even if you get a memory dump, it won't be totally straightforward to see that relationship between the binary and the APIs. And as we will see later on, in the case of Tomaida and some others, they actually go to great lengths into trying to obfuscate the fact that they're using APIs, and they would use really interesting tricks to make it non-obvious. And you will see that there's no straight jump into the APIs by themselves. And there's a whole category of anti-debugging tricks, which are aimed at making your life using a debugger as hard as possible, like making tracing hard by constantly triggering exceptions and making it really hard to step through the application, doing timing checks. So if they see that a certain algorithm is taking way too long, it could be because you're stepping through it, so they may actually misbehave later on. If they notice that the timings are not right, are not what they should be for a certain CPU, if it will be running natively on it. Other things, throwing interrupts that the debugger uses itself, and if they cannot capture it, the application cannot capture it because the debugger is running, then you know that something is wrong. You are being debugged. Then you can use, if the debugger is running in user mode, you can just use straight syscalls, which won't be hookable by the debugger running in user mode. You can check for hooks. You can just, if you have checksums for APIs, you can just scan the normal APIs in the DLLs and see if they match, to see if the debugger installs some sort of hooks. You can do a set of, there are millions of techniques to try to detect debuggers, user mode debuggers, and kernel debuggers, looking for strings, looking for softies, looking for certain drivers. There's a whole encyclopedia of those. So this is basically what we have got so far at the level of anti-debugging. There will be anti-environment techniques, which would be in certain companies, like antivirus companies, for instance, or anybody pretty much doing something with malware has a couple of VMware or other virtualization software boxes where they actually, at least do some sort of pre-analysis to take a look at it, or run it through some sort of behavioral tools that capture the APIs it uses to get a quick idea of what the malware might be doing. So in that case, lots of malware nowadays do actually try to detect virtualization environments, do the typical blue pill thing, or go into a little bit more complex techniques, trying to detect specific instructions that might not behave the same in a real system as compared as in a virtualized system. Certain instructions might be invalid in a real system, but might not trigger the corresponding exception if you run it in a virtual environment. So there's lots of things that are not perfectly emulated that you can try to use to detect a virtual environment, a virtualized environment, in which you might be being studied. So as a piece of malware, you want to avoid being studied, so you want to detect any kind of environment that could be controlled externally. Then we have the techniques against specific tools, as I just briefly mentioned before. If the tool is a debugger, then you can have all kinds of techniques trying to detect it, whether its presence in memory. If it's a tool like AIDA, for instance, then you can have specific techniques to make the disassembly, for instance, harder, or in the past there were problems where you could actually break the PE parser depending how your PE headers were constructed. But that problem was fixed. Some of the analysis problems are just hard to fix by themselves because it's not decidable entirely whether it's one thing or another. It could be disassembled in different ways, so you just have to know the right one when you're working with it. So you can try to break all of these tools, break others like ProcDump and SoftEyes. You can actually, some of the old ones like ProcDump, you can actually break them by erasing or once you're loaded in memory, writing different values in the headers in memory. So when ProcDump trusts the headers in memory to the dumping of the process. So if you put really large values to some of the sections, ProcDump will try to dump 2 gigabytes of memory and probably not be successful. So it will crash. So that'll be another set of techniques. Then we move into the more interesting stuff, which is anti-analysis. Anti-analysis will be something that is meant, whether you are analyzing the application, like with a tool like IDA, or even a debugger. This will make the actual comprehension of the application harder, just because they insert junk code. So between like a small function, you could end up with a really, really large function with the same functionality, with a lot of useless code, but not obviously useless code. You will see operations being done. In the end, they will cancel out, but it's not obvious for a human as seeing the assembler that will cancel out. You will need automated tools to actually simplify all that out. Things like using opaque predicates, for instance. I will cover that later, so I won't go into detail now. But that will obscure the execution, the flow of the application as well. Then there will be things like code transformation and virtual machines, where the actual code of the application, the code that you're seeing, is not the code of the real application. It's the code of the CPU that emulates a real application. And we'll go into that into detail later. And then other techniques that do flow obfuscation. One thing that you do, and that's very common, is using exception handlers to divert execution. So when you're trying to debug the application or walking through it, you won't see the normal flow, like just a call, a jump, a normal branching. The flow is directed or is controlled a lot by throwing exceptions, like call a specific exception handler that you need to know what it is. That exception handler might do some other techniques trying to detect something, doing some checksumming. I mean, you can put whatever you want there. Some Packers do checksumming on their own code in the exception handler to verify that everything is coherent in memory. And but it makes it harder to follow because it's not just a continuous like flow of instructions. It goes jumping all over the place. Other things like Armadillo's nanomites, which I will cover in detail later, it's a really nice technique and makes the flow analysis itself kind of much harder. So for what I'm going to be explaining later on, the tools that I've used that allowed me to look into this at a high level enough to not have to worry about the small details and the anti-whatever techniques, where Box, I use this a lot, is a full CPU emulator. So it gives me like a really, really high-level view of everything. The only problem is that I need to work and remove all the stuff that I don't care about because I see everything. I see all the OS, I see all the kernel executing, I see every single application. So I need to have some infrastructure to just focus on whatever I want to look into. But the good thing is I don't need to worry about lots of VMware detection. I don't care. Virtual PC detection, I don't care. Not that they couldn't detect Box, but nobody's been looking into it so far, unless in depth. So I can run armadillos, Tamidas, whatever, and they just run fine. So that's really cool. So you can trace them, you can do all kinds of in-depth analysis of them. WinDebug as well is one of the more powerful debuggers, and it's extremely useful to just hook into the kernel mode, debug, and then you can look into applications that are really, really low level of granularity. As well, it deals extremely well with complex exceptions, things that Oli cannot really handle. I was sometimes looking into Armadillo, and in some parts of the code, just Oli cannot handle certain exceptions, cannot really pass them back to the application and handle them properly, while WinDebug didn't have a problem whatsoever. And if you're really hardcore, you can use Peter's Memorize. That will allow you as well to get the real dump of memory and work with that a little bit in the same way that the kernel level access of Box or WinDBG give you. So all of those are really good tools to play with stuff at the low level. Both, well, as you saw, Memorize can actually give you physical data, like freely from the physical address, as well can WinDBG and Box, and that's a really interesting aspect of exploring the machine at the physical level. There's lots of tricks that don't matter then. So now I'm going to move a little bit more into detail and explaining some of these tricks, some of the more interesting anti-analysis and obfuscation tricks. So most disassemblers will actually have some sort of logic to go through this assembly, obviously. So they will collect a set of entry points of the application and start disassembling them. And whenever they find branching instructions, they usually put them into a queue and process them whenever they finish with a sequential part of code, right? Whenever they find like a unconditional jump or a red, they know, okay, I'm done with that chunk. Let's see what I have in the queue. And then as you disassemble, you keep adding all the conditional jumps, all the calls, whatever, into that queue. So eventually you process everything that is referenced from the code you started from. You can try to disassemble a little bit further, but like disassembling after reds and jumps, you know, might or might not be code. So you have to be a bit careful with that. So the problem is, depending how you handle this queue, just imagine, just disassemble sequentially, you find a conditional jump. Okay, you can start disassembling after that conditional jump. Normally there will be proper code. But if the conditional jump is always taken and goes somewhere else, that overlaps over that code. That's what I'm going to explain a little bit. It's complex because if it overlaps, if you take one branch, you see one kind of code. If you take the other branch, you see another kind of code because it overlaps. Only once it's going to be taken in the end. But it actually leads to different code. So for an analysis tool, that's hard to decide. You know, if one is obviously non-code, yeah, you can say, okay, I'll drop that. But it might not be totally obviously non-code, so it's hard to decide. And so it results in confusion for most tools. So one of the things that IDA makes is really powerful is that it's interactive. So you can decide when you are analyzing what is what. Well, other tools, you cannot really do that. And only you really have to go there and tell it to analyze a specific part, while IDA is a little bit more versatile into that. And then another side effect, this is not necessarily a tool for obfuscation, but it works like that, will be heavy optimization. And just have an example of that later on, which nowadays compilers, if you go to extreme levels of optimization, make the binary really, really nasty to look into. So one thing that, if anybody has looked at ASPAC, that just like comes like at the first thing at the entry point and goes a little bit into this decidability of what branch to take, right? So if you disassemble this sequentially, this is the original set of instructions, after the call, and you know, normally code follows after the call. So you want to continue disassembling. It's not a non-terminal branch. Normally call returns and there is something after that. So if you disassemble sequentially after the call, there is a jump. But the jump goes not really anywhere. It's an invalid address. But you see this +1 in the end. That +1 means that it's jumping into the next instruction +1 byte. But the disassembler in this case, either the last version actually handles this properly, but in the older versions didn't. So if you disassemble this sequentially, which would be one of the most obvious things, you see that this call doesn't look too nice. So the right way of disassembling this, but it's hard to say unless you know it works like this, is just like not disassembling the next instruction and going to where the call points to, and that's the real instruction, and that's a proper jump. So that's one of these anti-analysis techniques that actually is aimed against the analysis algorithm of the tool, of the disassembler in this case. Another case would be this linear disassembly. Again, we have a similar case, jump +1 instruction. If you follow straight, you'll disassemble the jump. Here you will have to leave, jump over that instruction to get to the final destination. A more interesting case, though, is the opaque predicate, because again, we're a little bit like in the case of the call. We cannot decide after the conditional jump whether to follow one branch or the other. So if we continue disassembling after the first conditional jump, we get into another conditional jump which looks like it should be the real thing. But if we actually would follow the reference first, we'd actually get to that move, which is the actual real code, jumping over that thing. And as you can see, the condition always evolves to true, so you will always take that jump. So when you use all these techniques all over the binary, make the flow a little bit annoying to follow, as you can imagine. And some of the Packers use these techniques, reassembling binary code using this all over. So you get like really small functions blown up to something really large where the actual flow is really obfuscating, and most tools cannot follow it properly. So even it's really large, it's not even contiguous. You have to make a lot of manual work to get it to look nice. Then moving on to the side effect of heavy optimizations, this would be like normal functions looked in a normally compiled binary, where you would have a function in a contiguous area of memory. You would have all the chunks, all the basic blocks of the function always together. But if you use heavy optimization, if you use what is called profile guided optimization, so that the application is compiled first with instrumentation, is run over a certain time with the common use cases, and that statistical information is used to later on compile the application for the commonly troubled areas to be together in memory. That saves time because all those blocks will be together in memory, needs less paging, it needs less cache in the CPU because all of these frequently touched basic blocks are all together. Then you will end up like in situations like this, where a function is split all over the file. Most tools won't have a problem if you're working with the graph view in IDA. It will pull the chunks wherever they are in the binary and show them together. But if you're in the text view or in any other disassembler, you will have a basic block, you have a reference some other place in the file with the next basic block, so it makes it kind of annoying to work with. And that's just a side effect of optimization. Then further optimizations, which I've seen in the Microsoft compiler in their own binaries. I haven't managed to get these working with the official version of the compiler, which is the case when you get shared basic blocks. When the compiler started doing all this splitting, it actually realizes too, in some cases, that the ending of some functions is the same. So instead of repeating those last basic blocks, it actually points different functions to the same set of basic blocks, which is usually just a couple of basic blocks restoring something or doing some error notification and returning, because well, it has to be the same flow for both functions. But again, this is really annoying because at least I think to one of the last versions, the algorithm cannot assign certain basic blocks to more than one function. So you will get blocks that are split but won't appear in some functions view. So you will get missing parts of code. Well, not missing. If you follow the reference, you get there. But the logical view is not necessarily totally correct. And this is not necessarily a technique made against analysis, but it just happens to make it a bit harder. Then we move into the addition of polymorphic and static junk, and we will see that in a case in Temaida. Good hints of finding junk usually is like the push A and pop A. These instructions save all the registers and restore all the registers from the stack. So it's used commonly whenever they insert junk to save the state and restore the state of the CPU. And so they will just like store it or save it and put a lot of crap in the middle, like 2 instructions, whatever. So something that looks like it could be code. So the analyst cannot tell it for sure whether it's junk or not. And then in the end, towards the end, do a pop A. That's the easiest. It's kind of easy to tell that there's something like that going on when you see these 2 instructions. And then as well for junk code, or it's still very annoying, would be the constant branching. Like I've seen obfuscators that take a piece of malware, take a function in a piece of malware, and they will get every single instruction, put it in a place of the binary, do a jump through a table to the next instruction in that function. So you end up with like function, could be like 20 instructions. With all the instructions split all over the binary, it will jump. So it's really annoying to look at that because you don't see it contiguously at a single time. So as an example of this obfuscation, this is a small chunk of Temaida. And Temaida is like breaking obfuscated functions all the time with jumps. So in this case, you can see there is a deck in the beginning, there is a push all, so he's saving all the registers, then he moves something into ECX, push ECX, then saves the flags, then jumps somewhere, which is in the top here, jumps to a jump that then jumps somewhere else, and that somewhere else, the only thing that restores the flags, pops ECI, and then pops all overwriting ECI. So all of these did nothing other than jumping around, except the first deck that decremented EAX by 1. But the rest, nothing happened. So whenever you get lots of these, and you get lots of this, it's really, really annoying to look at the code. In some cases, it's more or less obvious. In this case, you could even script it, finding the equivalent number of pop-alls and pop-alls, so that you could try to decide, okay, I've seen the same number of things, nothing happens in the middle, there is no memory writes, so I could just like optimize all of this out. But in some other cases, it can be a little bit more complex to decide whether it's junk or not, so like, at least within a script. So that would be like simple examples of junk code insertion. And these obviously can be polymorphic. You can have certain routines that generate these do-nothing operations, so in every run of the application it looks different. Then moving into what has become lately the more fun part to work on with malware protection, which are virtual machines. And virtual machines, it's a relatively old idea, and their implementation in malware doesn't really bring anything that much new, except that it makes it really hard to analyze. So virtual machines, they exist in Visual Basic, Java, Python, Ruby. It's basically you get a language that gets compiled to some sort of bytecode, and that bytecode gets interpreted. So protections using these are StarForce, VMProtect, the x86 virtualizer, which is a really nice example because you have the source code for that in OpenRC. So the x86 virtualizer, it's like full virtualizer, uses lots of really nice techniques, and you have the full source code, so you can, it's really interesting project to look into if you're interested in understanding well how virtual machines work. And then obviously Themida and Cold Virtualizer, which are famous within the malware world just because they work really well and make the analysis a little bit nasty, a little bit hard. So the basic working of this is the code gets compiled or transformed into code for the virtual CPU, and what you end up seeing in the malware is an emulator or the implementation of the virtual CPU that will go fetching all of the virtualized instructions and executing them. So you will see these like abstract CPU running, but you won't see the original application. Well, that too, but a different abstraction layer. So it makes it really hard to comprehend an application. What you are seeing is the virtual machine running, getting an instruction, processing it. Doesn't make it much really obvious. So basically all of them end up being like a fetch the code and handle algorithm, and there are certain patterns that you can see on the virtual machines. The idea would be something like this. In a normal application on the left, it would be the standard code running on top of the real CPU. That would be the assembly code you see when you disassemble the application. So it makes it really, really easy to see, to just read the assembly, that's it. For a virtualized application, you would get the virtualized code that would run on a virtual CPU, and that whole environment emulated would run on the real CPU. So what you are seeing is the virtual CPU emulating stuff. And the general layout of this is pretty much generic to all the implementations. The virtual CPU, that would be the program that runs, at some point would get passed originally in the beginning a pointer or indicator to where the virtualized code starts. And then it would go and fetch that instruction. It would usually uses the opcode to look in a table where the handler for that instruction is, where the actual code implementing the instruction is in memory. But these opcode tables can be, at least Themida encrypts the actual opcode to reach the table, so it won't be obvious finding the opcode. In something like, for instance, Visual Basic is really obvious. If you want to study the virtual machine, you'll find like a really huge table of pointers, and you will see that it's really easy to find where it's going next. In a case like malware, they try to obfuscate that as well. So, but the algorithm behind all of that ends up being simplified, something like this. It will go find the opcode, find where the decoder will find where the actual handler is. The handler will actually perform whatever operation it has to do, update whatever registers it has to do in the virtual CPU, and then the decoder, after the instruction is finished, it will increment the instruction pointer to go to the next instruction. That will be the red arrow there. So it will basically go through all these numbers all the time, executing all the virtualized code. So that's the process you would see in the assembly, which again abstracts a lot the actual application. So the attacks or the countermeasures you can actually try to implement against virtual machines, although it's a really, really hard field because there is no generic technique against all of the virtual machines, because each virtual machine can be implemented in a different manner, can implement a slightly different architecture. Take for an example Themida. Themida, when you pack an application, lets you choose between like 4 different types of processors, 2 CISC and 2 RISC, and all of them can have their opcodes randomized, polymorphic, so every time it runs it's different, like the slightly different architecture. So generalizing all of that at a high level so you could actually attack all of those, all of the virtual machines implementations, is hard, to put it mildly. So what some people have been doing, Rolf Rose actually has some really good articles in OpenRC, is translating the actual code, and actually Borislav actually was working on something very similar, had a really good paper. I have all of that in the references. So what you can do is translate the virtual machine representation. You need to study the instructions, you need to study all the handlers to know what they do, but translate all of those to an intermediate representation, and then use normal compiler techniques to optimize them. So eventually, and that's a technique you can use on the same lines against junk code. Just translate it to something and optimize it. Eventually, you will get a more or less canonical representation of the actual meaning, and most of the garbage will get optimized out, because eventually they will be adding and subtracting to the same register, or they will be modifying registers that will override later on. So all that is dead code optimization and dead variables, so all of that will be optimized. Another thing as well as talking about this memorize tool. Memorize? Memorize. Okay. That you can actually use it to find the handlers in memory. If you can actually scan, because the handler is going to be something, Temaida, for instance, unpacks all of that in memory. So in Visual Basic, that would be in the DLL and the real code. But if you want to find handlers, you will need to scan memory to actually find all these parts of code, because they might not be referenced directly. After all, they're going to be referenced through a table that the CPU uses. So you can use a tool like that to actually scan for all possible combination of code in the memory you dump to find all these handlers that will give you hints of where those are. But again, this is not like a solved problem at all, and the techniques you can use so far are advanced and somehow primitive, because you're attacking very high levels of abstraction, and but still would be translated to some other representation and do an optimization. If you have different translators for different CPUs, then you would have a common tool that would actually do the optimization for all of those. Like Vodislav did, their tool did Temaida and did VM Protect more or less generically after some translation, if I remember right. So virtual machines are, I would say, one of the toughest issues right now, just because of the way they obfuscate the code, and there is still no generic way against them. There starts to be some generic approaches, but it's still like reconstructing the flow, which would be one of the more interesting things. Reconstructing the flow of the abstracted application is not obvious, is not doable yet, and it will require a lot of computation, because you really need to go to the level of interpreting every single handler and extracting information from an analysis of that. So it's very computationally intensive. Then, well, I've been talking already quite a bit about this. VM Protect is another Packer implementing virtual machines. Armadillo has a different set of techniques that make tracing of application really, really annoying. So all of these, I guess this is needless to say, but all of these are commercial products, and to get to this level of sophistication, you really need to devote some time. So quite often these end up being like full projects, and people make money off them to get to this level of complexity. So I'm going to mention now some of the specific techniques to both Armadillo and Temaida. So one thing, well, Armadillo has one technique that I really like. It has been used as well in other places, but it's this double process debugging. So when you use this kind of protection, Armadillo has a set of protections. But when you use this protection, Armadillo, the Packer, is going to run. Then it's going to create another process that is going to create it as being debugged by the first one, by the parent process. So you cannot attach to the child process, because it cannot be attached by two processes at the same time. So the actual application is going to be unpacked in this child process, to which you cannot attach. And and obviously Armadillo is going to do all kinds of checksumming and tests, so the whole thing runs. So that's a nice protection, because either you trace the parent and remove the protection and then go for the child, or you cannot do, or it's a bit hard. And then the nanomice combined with that are extremely interesting, just because it's a way of modifying the flow going back from the parent to the child, and I'm going to detail that in a second. And it's interesting because it breaks the flow in the child, and as well makes the two processes very, very dependent on each other. So you cannot really touch one without, fucking the other. So you really need to be very careful how you play with this. Then another technique that it has is strategic code splicing, just call it like that, which is basically just getting arbitrary chunks of code of the application, putting them somewhere in random memory and executing there. So it's really difficult to dump it properly. I won't go into detail into that one. And one thing that Armadillo does while it's unpacking is throwing all kind of, using all kind of tricks to disturb debuggers. One that you will see is invalid uses of the lock prefix that can bother some virtual environments, just because some of them won't raise an exception for an invalid combination of a lock and an instruction, when a real system should do. And actually something I noticed when I was playing with Armadillo, and that was a really nice test for WinDebug, was that just after throwing one of these invalid lock combinations, lock instruction combinations, and you have to pass it. If you're debugging this, you have to pass that exception to be handled by Armadillo, otherwise something is going to break. And once that is done, you'll jump into a move. It's like, what could possibly be wrong about the move? So actually, that move that Armadillo was using was an invalid move. Was a move using an invalid combination of operands. So the thing is, it was supposed to throw another invalid opcode exception that was supposed to be handled by Armadillo, but Oli couldn't do that. Oli saw a normal move and couldn't handle that exception, as well as a few other tools that saw that as a move. Was really surprised that WinDebug actually handled that perfectly, recognized it as invalid instruction, didn't disassemble it. So that was a really nice thing for the disassembler. It was aware of that encoding was not valid. All the other disassemblers I tried did say that that was a proper move. And allowed me to actually pass the exception. So with WinDebug, there actually was not a problem to trace through that. But lots of other tools had actually trouble. So it's really nice when you hit something that looks like a roadblock, try different tools, because sometimes it's the tool's limitation when you're working at really, really complex levels or like really advanced techniques. One funny thing, though, is that that was not a problem. The invalid move was not a problem in any of the environments that I run in normally, except in Box. Like VMware, all the others run it and throw the exception properly, but not Box. So I've always wondered, although I asked the guy who brought Armadillo, and he told me he didn't explicitly make that for Box, but I always wondered if it was against Box or some other sort of like full emulator, because a move, you know, it's such a basic instruction that either is executed by the real processor or there has to be some sort of trick with the emulators. Because otherwise, like an Intel processor or most of the virtual machines are going to throw an exception to that, because they will run it natively. There is nothing to it. So it was an interesting case to, you know, make you think of how crazy these guys go to implement all kinds of tricks to break your tools. So now I'll detail a little bit this nanomites thing I talked about. If this unfreezes, come on. Must be because I have pretty pictures on the next page and doesn't want to show them. So, while this decides to pass, oh, nice now. This details a little bit of the nanomites technique. So, to recap a little, the idea is you have a parent process debugging a child process. So you cannot attach to the child. The nanomites, what it does is obfuscates the code a lot by inserting in, for instance, conditional jumps. Instead of the conditional jump in the unpacked application, it would actually insert an interrupt, an in3. The in3, obviously, when it's like reached in the child process, will go to the parent process because it's the one being debugging the child process. What the parent process will do is like it will see where that interrupt was thrown, at which instruction, will look that instruction into a table, then it will look at the E flags to see what condition, what was the condition and where it was supposed to go, like true or false. And then it will restore the child process with the actual target where it was supposed to go. So when you're actually studying, if you would be studying the child process alone, you will see that it throws an int and eventually appears somewhere else, but you wouldn't see how that flow went there. It's going through the parent that looks it up into a table and then restores the child to be there. So it's like a really interesting interaction between child and parent process. And in the child process, if you would be able to do a dump of the child process, you wouldn't see all the flow, because you could actually end up doing ints for half of the code. So eventually you would have half of the instructions missing that will exist only in the parent, or through the parent, because it will just make you go wherever it wants you to go. So it's a really interesting interaction. And with a tool like Box, it's not a problem to dump and to look into this, because you don't care about who is debugging what. You're at a higher level, or a tool like WinDebug. But if you're with Oli, try this, because you really have to be careful. You have to do it by hand, basically. You have to look at the trick, disable it, and work one and the other. So that's a really good, cute process or technique, these nanomites. Now I'll talk about some of the things that Temida does. One that I really like is how it obfuscates APIs. The algorithm is really interesting, and if you do a dump of Temida, well, if you can, you know, if you can handle that, because they tend to be rather large. You will see that wherever it would, if you use the API obfuscation technique, wherever it would actually call an API function in the original code, it doesn't anymore. It actually calls some code that looks kind of messy. What Temida does, it actually gets the code of the original API in the DLL and reassembles it, inserting a lot of junk in the middle. So it would do the same thing, but it won't be in the DLL. So you won't ever see, if you hook the DLL or something, you won't see a jump to the DLL. It's somewhere else. So, and it will look like crap. So if you try to actually disassemble that, you'll see it looks really messy. So the whole process can be like explained visually like this. Normally, the normal relationship between an executable and a DLL is the executable will be importing some symbols, and there will be a set of pointers put towards the DLL function. So whenever the call to whatever imported function is made, is redirected to the DLL. So specifically in the case of one function, just imagine that exported function from a DLL. Exported functions sometimes, if they do something more than just like setting a value, they are related, they have references to other functions. I'm explaining this because of a technique later. The exported function will reference other functions within the DLL, and that arrow to itself is because it will have conditional jumps pointing within itself and everything. It's a normal function. It will call other things. We will use that in a second. So that would be how it would look, right? So what Temida does is just gets all the exported function and reassembles it somewhere else in the address space of the process, but heavily obfuscated. The thing is, I left those arrows there because Temida, I don't know if because of some limitation or because they don't want to go further. It will get really messy if they go further. The conditional jumps, some conditional jumps at least, within the obfuscated DLL still refer to the original DLL, and that's something we can use. As well, references, calls to other internal functions within the DLL are kept in place. So if you look at the obfuscated code, if you go step by step and look at all the obfuscated code, you will see that eventually there is a jump that goes back to the DLL, or a call that goes back to the DLL if there is any function from the DLL being used. So that's something that we can use to try to figure out without undoing the obfuscation what actual API was that. So this is basically what I was going to say. This connectivity, the fact that it still refers to parts of the original DLL is something we can use to guess what DLL it was just because of the references. If we study the DLL and see that only one of the calls, exported calls, has the same references, which tends to be the case, then we know that that was the DLL call without actually even looking at the code of the call. So as for the obfuscation, it adds a lot of branching and junk. It's really impressive. As I showed later in that example of Temida, lots of jumps and lots of things that do nothing. Usually, if you're lucky, you see one instruction of the real function per block, but usually there is less than that. There's like one every 3. So one thing is, IDA can easily handle most of the branching, so even if it's obfuscated, you can recover and see most of it, but it breaks whenever you get a call. Because Temida as well, to do all the branching, uses calls that are not real calls, it's just to divert the flow. And IDA tries to assume that that's a function when it's actually not really a function. So IDA will just like break the flow there of the function, but you can actually force it to not do so, and then you will get the whole body. And you could even script this because all of this flow reconstruction is not too hard. What would be a bit hard is the optimization of the call. But if you just want to reconstruct the flow, that can be done. And this is actually how it looks like. This is from kernel 32. This is a get module handle. The one in the right is the original one. The one in the left is the Temida's obfuscated one. It does exactly the same, but with a little bit of messiness on it. And this was using the minimum settings for obfuscation, because I've seen things that wouldn't fit on the screen, like not really small, because it just adds arbitrary amounts of garbage on it. So actually, let me just, because I have this function, just to show you those things I was talking about. So let me see if I have the, yeah, this will be the original one. Let's see if I can. And I will just highlight this location, just remember the 54C. And if I go to the obfuscated one, you'll see like it takes quite a while to get to this part of the code. again, the move EDI is in the original function, then starts garbage. All of this is mostly garbage. Follow the jumps, garbage, garbage. Takes quite a while. Every now and then there is like one real instruction, but eventually we'll get to the conditional jump. Yeah, here it is. Here's the compare, just before the jump, which is the same thing, but without the name. And eventually here's the actual one. And if I follow this jump, you can see here that we are working on the address. Where am I? Here. I'm working on this address, 160, which is not the DLL address at all. This is code that is being copied and modified and obfuscated on somewhere else. So if I follow the jump, I end up in the DLL. I have all the code of the DLL because this is like an internal, like a whole dump of the address space of the process. So I have everything that was used by this process. So I can actually see the code of the DLL. So you can see this is the same addresses we have in the DLL, the 54C. So this is what I was saying about the references that are still kept. And actually later on, within the obfuscated code, we get a call to a function in the DLL. And if I go here, that's exactly the same as this one. These two functions should be exactly the same. Or I got the wrong one. How many calls are there? Ah, no. It's this one. I went ahead. Yeah, with a little bit of imagination and with our names, you can trust me. That's the same one. So that's how the obfuscation looks like. As you can see, Tomaida does a quite good work making things look bad. So let's keep going. So, summing up a little bit what we saw up to now, the battle between packing and unpacking is like, I have some friends that are still trying to do like perfect unpackers that reconstruct like the original EXE, and I just think that's kind of a little bit of a waste of time, because with the hardest packers, the application is modified in such a way that I think is extremely hard to consider that you will be able to restore the original application, like the original binary. I think that that's something that eventually, if the packers advance enough, won't be possible. It doesn't mean that you can get something that could eventually run or it can be easy to analyze. That's another thing. But I'm not anymore aiming at getting an original EXE with a nice import table. I'm more for getting a working dump with symbols. That's all I need usually. So I think that can be done, and that will be possible for a long time. I guess even with virtual machine techniques, you can do quite a bit of things with the scripting and optimization working on a dump. So I think generically all of this can be done. Like I'm writing generic unpackers for quite a while, and I don't see many problems that I'll be able to do it in the future. I see some technical battles, but I don't see that it will become impossible to do. Reconstruction, yes, reconstruction can be, it is a mathematical problem to reconstruct something that has been extremely obfuscated into an original form or a reduced form. Can be optimized, but I mean, reconstructing it back to the original form, that's another thing. So I would say that yes, you can get close to an original form of the code, but not necessarily restore the original application. And now I still have some time, can have some questions, but I just like to cover this. This is really recent, like a couple of weeks ago, Escape mentioned a technique against generic unpackers, or some heuristic that generic unpackers use. And the heuristic is the one of tracking dirty memory. And a basic way of displaying this would be like originally when the unpacker is going on, when the unpacking is writing to memory, you get like a virtual address, then the code is written, that will be the second block. The code is written, and eventually execution, that will be that arrow coming to the written block, that will be the execution going there. So that's basically the the algorithm of an unpacker, very basic unpacker. You know, just get the memory, you start decompressing or unpacking the application there, and eventually give it the execution. So you can actually track for this. That's what lots of generic unpackers do. They try to monitor the memory whenever see that the execution goes to dirty memory. It's like, ooh, that's interesting. You can do a bit more advanced heuristics because this is not totally foolproof, but you know, it works. So what he did, and that's a really cute idea, I believe, was using the memory mapping unit abilities, or like what Windows provides. You can actually map two virtual address ranges to one physical memory address range. So you would have two different address ranges within your user mode application that map exactly to the same physical memory. So you could actually write to one of these and execute from the other. So you will break this heuristic of detecting, because you will be writing to some area of memory, which could be anything, it could be data, and there will be never anything executed from that area. You will be executing from another area, but all of these are the same. These two things are the same. So any modifications you do to the one appear in the other. But this is really cute because it breaks this technique. But if you are playing at a high enough level, if you're working at a kernel level, you can actually study the page directory like the Memorize tool, and I see that there is double mappings and things like that, which are not necessarily a standard thing for most applications. So that would, you know, ring something like, there's something weird going on. So, and low-level emulators, anything that gives you access to the memory mapping unit, should be able to detect these things, but still most of, or all of the user mode generic unpackers would be tricked by, that use this technique would be tricked. So I found that really, really cute. And one last thing that I want to show before I jump into the references is like talking about visualization. Just to give you an idea of the complexity of like a Temida when it's running in memory. Let me show you if you can see this properly. First, let me explain you what you're looking at. This is a representation of a memory dump of the address space of a process when it was unpacked. So each of these blocks is a memory page, is 4 kilobytes. The color and what you will see now, the height, is the entropy. So the higher or the redder the color, it means that it's more likely to be code, for instance, or it's to contain high entropy data, which, yeah, usually either is code or is some sort of compressed data. So this was Notepad packed with NSANTI. And if you can see the pointer, actually Notepad is just this thing over here. The actual code is just those things. The rest is just like heap and stack. So just to get an idea of the whole layout. I mean, here we can see the higher points. The red points are the ones with the highest entropy. So these would be where compressed data might be. The rest that you can see is all over are areas containing different sets of data. Could be text, could be just random, arbitrary data. So this is NSANTI. This is Notepad. Now you're going to see Notepad with Temida. So Notepad is still that thing over there. The rest is Temida code, obfuscated code, temporary code of the virtual machine protected malware. So again, you can see this is quite a monster. It turns an application that is like 60 kilobytes into something that's like 1.5 megabytes, and most of it is Temida's own code, and obfuscated code from the API. Remember that it will pull APIs, put them in this address range, obfuscated. So that's what you're looking at. So that's the level of complexity in Packers that we're seeing nowadays. So with techniques like virtual machines, techniques like hardcore obfuscation and flow obfuscation, anti-analysis techniques, it's going to be much more work for us, I think. So after showing this, I think I just want to quickly walk through the references. Whenever you get the slides, whenever they're on the site, I put like 4 slides in the end with the references. These are really worth a read if you're interested into this. Really good papers on malware analysis, on virtual machine analysis, virtual machine detection, Escapes article, Vorislau paper on virtual machine virtualization techniques, extremely good. Rolf Roll's articles in OpenRC, really, really good about using optimization techniques against virtual machines. Then Orient site for Tomaida, they have some technical info about the thing. Rewolves, that's x86 virtualizer, that's the thing in OpenRC. If you like to study virtual machines, really good thing to check. And if you want to read more about nanomites and you can read Serbian, then I would recommend you the Rocco's nanomite write-up. Just Google Translator if not, that gets the work done. And then Memorize, that's a kick-ass tool that he wrote as well with his team. So that's another thing you gotta check and try because it's gonna help you to do lots of these things. And well, I think we have 5 minutes left. I would like to thank the Hack in the Box team and Dylan and everybody that came here. Hope you enjoyed. And if you have any questions, please fire.
Any questions from the floor?
Was I that good? Yes.
As usual. Well, thank you very much, Ero. Thank you for taking the time, and we really appreciate having you down here.